We will consider the third type of force, intermolecular force, which is dipole-dipole interactions. So let's consider the hydrogen fluoride molecule that we had before, and we have the partially negative and partially positive ends of the molecule, which constitute the dipole. Well, we can have an interaction between these molecules, and there are a couple of different ways which we can arrange these molecules. We could have an interaction in which another HF molecule with its partially positive and partially negative ends lining up so that there are attractions between opposite charges on the opposite molecules. So this is a classical arrangement of two dipoles. We could also have an interaction in which the hydrogen end of one fluorine can interact with the fluorine of another molecule. Oops, that's supposed to be a negative. And so we can have this interaction between opposite charges. Now if you look at this particular arrangement, there's only one interaction here, but there are two interactions in the molecule above, and it just depends on the relative strengths as to which geometry is the most stable. So it's not always easy to predict which geometry will be the most stable for dipole-dipole interactions. Let's consider a nonlinear molecule, say the water molecule. And we have an oxygen and two hydrogens, and if we look at the electronegativity differences, the oxygen will be partially negative, the hydrogen's partially positive, and so this will constitute a dipole, where this is the positive end and this is the negative end of the molecule, and two oxygens can interact. So I'll draw them sideways here. So we have a water molecule here. We can have an interaction of, say, the partially negative oxygen with a partially positive hydrogen of another water molecule. Now there are various ways these can interact, various geometries, and it just depends on their relative strengths as to which geometry is the most stable. Another possibility would be, say, have our water molecule with the positive end here pointing down, the negative end pointing up, and then we could have an oxygen maybe interacting with these two hydrogens of another water molecule. So we would have to do specific calculations to determine which of many geometries is the most stable. So it's not easy just to predict from drawing pictures or off the top of our head. Now one thing with water that's special, and I've drawn it in such a way that previously have a water molecule, and the oxygen can interact directly with, oops, it's supposed to be a bond, can interact directly with the hydrogen. So this is a partially negative end, partially positive end of another water molecule, and this is an interaction. And when we have an interaction of a hydrogen, it's partially positive, with a partially negative atom on another molecule, this type of interaction is given a special name, and it's called a hydrogen bond. Now this is not a real chemical bond, it's just an electrostatic interaction, weak compared to a chemical bond. that it's just bonding between partial charges. So we have a partial negative charge here, a partial positive charge here, and it's the attraction between those partial charges. And when one involves a hydrogen atom with an electronegative atom, it's called a hydrogen bond. So water has hydrogen bonds. And this is just another form of the dipole-dipole interaction. Now the strength of the hydrogen bond can be predicted by the relative electronegativities of the atoms. So let's now consider hydrogen sulfide, which is another molecule similar to water, and it can also undergo hydrogen bonding because it's supposed to be a sulfur atom. So we can have partially negative sulfur, partially positive hydrogen all around, and we could have a hydrogen bond right here. However, because the sulfur is less electronegative, then the partial negative on sulfur is going to be smaller. So the sulfur partial negative is less than the oxygen partial negative. So the hydrogen bond will be much weaker between hydrogen sulfide as it is with water. This will affect the physical properties of the two molecules.